Welcome back to another video in the series. This time we're going to be looking at types of systems, and I've tried to write this out already, so then it will mean less writing, and hopefully the videos can be a bit more efficient. So there's three types of system I'm going to talk about in this video. We've got dynamical systems, we've got control systems, and we've also got hybrid systems. So the first is dynamical systems. So in all these cases, we can describe our system by a set of equations. So here I've got a set of equations representing the evolution of national income, I believe, from America. And so this set of equations has kind of three equations here: the output y, which is based on C, I, and G. And then we've got these two components, these two equations here, which define how the system evolves over time in different time steps. So C evolves by some value alpha multiplied by the output, and I evolves by a value beta multiplied by this equation Cn plus 1, subtracting C. And we can simplify this equation so that on the left-hand side we have all the terms which signify a time step in the future, and on the right-hand side we have all the terms that relate to the current time step. So this system here is just equivalent to these two equations, where we've got alpha times C plus I plus G, and then we also have the next step of I equaling beta multiplied by alpha times C plus I plus G, and then also again the C term being subtracted. And you can check for yourself that these two are equivalent. So we can write this system here, this two-dimensional system, using our approach which we've discussed in previous videos. So we can imagine that this is an infinite space system. So we can define a set of states x which are in the real part, positive real values, including 0, and there's two dimensions, so this is squared. We can say that the initial set is equal to the full state space, and for the inputs we define an input star, and so this star just represents the next interval, so just advancing the system forward one step. So our transition relation then will be a set of transitions where we start in Ci, and then we advance the system forward one step, and we go to some new C dash I dash state. But only if and only if it's the case that this new state C dash is equivalent to this equation here, if it solves this, and similarly only if I dash, or the new state I, equals this right hand side of the equation. We can then also define our outputs. We have the equation here, y of n is C plus I plus G, so we know that it's a positive real value within the set of reals, and that mapping we have is just equivalent to the right hand side here. So we can also do this with continuous transitions, so we can treat time being continuous here, and we can treat time as the input to the system. So we can have some state x with a time step tau, which transitions to a new state x dash. And so this transition will exist in the system if and only if this initial state x exists already within the state space, and then if like the state space, this state x dash also exists for the state space at time tau steps, tau in time later. And so so dynamical systems, we can just measure how they evolve in time, but we're not able to interact with them in any way. So this is where control systems come in. So control systems, we consider that some part of our equations we have control over, so we can select the values. So here I've got a set of equations in continuous time, which represent Euler's equations for rotating dynamics with some inputs. So V1 and V2 are the inputs to this system, and then we have different coefficients I1, I2, I3 in the different equations, and then we have these states epsilon 1, epsilon 2, epsilon 3. So again, we can describe this system here. So we can have the set of states x are defined in the set of reals, and we've got 3 states, so we cube. The initial set of states is again equal to the full state space. And then our set of inputs now we're going to define as this kind of like funky U. So this is basically a set which represents the choice of curves that we can use as inputs. And so then we can again, now we have our transition relation, but this time we have the inputs that we can choose for the system representing that transition. So we go from some state with an input to a new state x dash. And so for the control system, we add on this requirement that this is only possible if there exists some input v, which is part of this set of curves, where v transitioning over the time step tau will give us these inputs v1 and v2. So there's 2 here, so r squared. And also if the state space transitioning from 0 to tau gives us some state in R3. And also this transition here, all 3 of these equations must be satisfied. So the state x from before is represented by a tuple epsilon 1, epsilon 2, epsilon 3. And so then the next time step of epsilon 1, epsilon 2, epsilon 3 must be satisfying this set of equations. We can set the output to just be equivalent to the state space, and we have a mapping which is just the identity. And so now the inputs are both the contributions of V and also the length of time that they're applied for tau. The final system then that we're going to look at is a hybrid system. So hybrid systems, these combine both discrete and continuous dynamics. So let's take this circuit here. This is a DC-DC boost converter. And there's this switch here which we can move from position S1 to position S2, and this will change the circuit. So for our hybrid system, the discrete parts of the system are basically the choice when we switch the location of this switch. So when we use input U1, we're going to push the switch into position S1, and the system will behave with these dynamics written here. However, when we give it discrete input U2, then we move the switch into position S2, and then the system will behave in a different way. And you can see that this system behavior here is in continuous time. So now we have a hybrid system because we've got discrete events which are happening, as well as continuous dynamics which are occurring underneath the system. And these change depending on the location of this switch. So we can define the system in almost the simplest form. So we have the system, and it has a set of states x, a set of inputs u, and some transition map. So our set of states x are now the discrete parts, so S1 and S2 representing the position of our switch, and then also 2 parts which are in the set of reals. So these are our 2 states, I to the I underscore L and V subscript C. For our inputs, we have our 2 discrete inputs, U1 and U2, and then we also have an input for the continuous parts. In this case, that's time, so just positive real time as it's a continuous system. And so we have these transitions where we have the switch location S, and the current I, we have the voltage C, with some input U going to some new state. And here we have 4 conditions for how that system will evolve over time. So in the first case, when U is U1, then we say that the switch in the transition should be switching to position S1, and that then I and V can kind of evolve as normal, or they're only the switch is changing here. The dynamics themselves are remaining the same. Similarly, when we set the input to U2, I and L, IL and VC will remain the same, but the switch will change to position S2. However, when we set the input to be this step in time, then the continuous dynamics will evolve. And so what we're saying here then is that the switch will stay in the same position, and that there should be a solution to these equations 1 and 2 such that the initial state here, IL, VC, should exist at in the first location, and that under this transition U there should be some new state, I dash V dash, that also exists. So when we're in S1, then we solve these 2 equations. And then similarly again, when we evolve the system in time, but S is in S2, then once again we should find a solution to this transition, but this time solving which abides by the equations 3 and 4. So this was just a very simple overview of the different systems that we'll be looking at in these videos: dynamical systems, control systems, and hybrid systems. See you in the next video.